So this makes the solution sets to polynomial equations closed. I'm trying to describe a rather exotic topology on Kn.
Okay.
This is called the Zariski topology. I think it gives us another nice example of a kind of unexpected topology on things that we know. See, because here K could be the reals, it could be the complexes, right? I mean, you could look at it a finite field even if you wanted to. That's what makes this so interesting, is that this setup is in some sense field independent, which makes it the natural way of looking at topology if what you're interested in is in equations independent of where the variables are attached to those equations. This idea about looking at an equation independent of the field is, I think, this notion of a scheme. That's part of it anyway. Algebraic geometry, as he's mentioning, is involving this kind of thinking. But it's more narrow than that. Getting to the point here. So the Zariski topology takes this as the basis for open sets. So, of course, wait a minute. Well, he wrote something here. I'm not sure what this means. You guys tell me. He says VE maybe. Intersection of F and E, VF. So here's this VF is VF here. So he says VF is the complement of DF. If you take the intersection over the complement for all F and E, what do you get? Say again? Yeah, f of a equal to 0 for all f in E. So yeah, exactly what you said. That would, so this he says the subsets VE are, as E varies, the only closed subsets in the Zariski topology. He says, given any subset E of the multivariate polynomials, one writes I equals to E. Sorry, let me write this down here. It says E subset of K x1 xn. Write I equals to E. So it's like generated by E. This is the ideal generated by E. What's that mean? He says E subset of I, and we have V of I, subset of V of E. Conversely, given any f in I, there is an integer n greater than 0 in polynomials f1 through fn. in E and G1 through Gn and K such that F is the linear combination of them. Well, anyway, I'm not going to do all of that, but he eventually gets to the point of saying that V of I equals to V of E. I think what he's getting at here is like a minimal set of equations which fixes the V of E. Like I is a smaller set of relations, possibly, that generates the whole solution set that is described by VE. Anyway, further, the Zariski closed subsets are precisely the subsets of the type VI as I varies among the ideals of the polynomial ring. So anyway, he's making a connection between the possible, basically the possible closed subsets of the Zariski topology correspond to the possible ideals of this. Now, finding ideals of a polynomial ring is a problem of abstract algebra. Of course, closed sets is a problem of topology, and they're starting to get intertwangled, aren't they? So, but yeah, this is one of the foundational things in algebraic geometry is working in the Zariski topology. That's the topology that's natural to study solution sets. And so, I mean, there's two different ways of studying abstract spaces, roughly speaking. Manifold theory, which is the parametric viewpoint. And then there's algebraic geometry, which is more versed in the implicit viewpoint. Algebraic geometry says look at abstract spaces as solution sets to polynomial equations or collections of polynomial equations. This is the implicit viewpoint. Manifold says hands-on, right? Here, I give you function, I give you a sample of what I'm trying to create, and I abstractly paste it up into this abstract set. That's a manifold. They each have their advantage. In fact, variety is typically this thing which is studied in algebraic geometry, right? So if you've had a lot of classes with me, I will talk about manifolds eventually, especially in advanced calculus. I don't really talk about varieties much because I don't know that much about algebraic geometry. But the interesting thing is the origin of the word variety and the origin of the word manifold, if you go back to Riemann's writings, they're the same word. So these two ideas were originally together. And of course, in Calculus 3, you experience that, right? I mean, we can either look at a surface parametrically or as a level set, right? You don't think, oh, those are two radically different. It's a surface, right? You can either describe it by an equation, x squared plus y squared plus z squared equals to 1, or by a parameterization, right? X of this, r of the standard angles, r cosine sine, or whatever it is, the usual fare. Once you abstract these things, they can look really, really different. But anyway, on my list of things to do, figure out algebraic geometry. And yes, you say it has to do with Fermat's last theorem and the technology which has been used to tackle that problem. I think that's probably fair. There has been a monumental amount of work done in algebraic geometry in the last century. Much of it by Grothendieck and his collaborators who, did this monumental amount of work in the mid-20th century. The Bourbaki, yeah. Do you know why there's some joke to be told there. But I think he only recently passed away, Grothendieck. He lived out in the countryside somewhere and he didn't want any of his work on the internet, which is really annoying because the internet, where you find stuff. But anyway, I digress. Wow, I really digress. So sorry. All right, I told you I'd get back to Gamelin eventually. The time is now. So where are we? So we talked about compactedness. Compactedness. We talked about connectedness, right? The next thing up was finite product spaces, right? So the section on finite product spaces, I actually covered the heart of this section in a previous class by accident because I covered my notes, and we talked about the order topology and that we proved the continuity of the projection map that day in the lab. That's like theorem 10.3 is let E be a topological space, f a function from E to the product, then f is continuous if and only if each pi j composed with f is continuous. That's okay. That's not what we proved, but it's awful close. Actually, that's a more interesting result. It says that the function is continuous if each component function is continuous in the abstract sense. Right. So this theorem 10.3 is actually more interesting than what we did. And theorem 10.4 is even more interesting because it says that if we have a Cartesian product of Hausdorff spaces, it's Hausdorff in the finite case, right? Theorem 10.5 says if we have a finite Cartesian product of path-connected spaces, they're path-connected. Theorem 10.6 says that the Cartesian product of connected spaces is connected. And then, let's see here, lemma 10.7 is a lemma. I won't read it. But that leads us to theorem 10.8, Tikhonov's theorem, finite case, which says that if you have a finite collection of compact spaces, then the Cartesian product of them is compact. Any of those things would be fun to prove in here. The next section is on set theory and Zorn's lemma, which of course states Zorn's lemma and a little bit about partial orderings and so forth. The punchline in this section is that every vector space has a basis. This, of course, is interesting because this concerns infinite dimensional vector spaces. So we'll get back to this section. Then past that's the infinite product space section, which punchline there is Tikhonov's theorem, which says that any product of compact spaces is compact, possibly infinite product, right? So the earlier section had the finite case, this has the arbitrary case. So that's where we're going. Probably will take me, I think probably next class I'll have covered a good bit. All I'm going to cover from that material next class, most likely. This is not on the test, right? As I said, the test stops where? I guess it stops at finite product spaces because we did that in class, right? Or no? I could say no if you want me to say no. No. Say no? Okay. So so up to section 9 then. So just the pages 1 through 90 and stuff I've covered in class, right? Any questions? So I think I'll just start with it next class. We've went over a couple of times. I think we should end early today, if that's okay with you guys. I think the likelihood I make some sort of egregious error if I try to prove one of those things in the next 10 minutes, it's high. It's very high today. I hope you enjoyed the Zariski topology. I think it's fascinating. I mean, it's not Hausdorff, among other things. You can't separate points with open sets in this thing. You start thinking, I mean, because what's open is the complement of solution sets to polynomial equations. What's that? It's not discrete? Yeah, the topology is far from trivial. But it's non-Hausdorff. Yeah. And I would say if you read people bemoaning algebraic geometry, something you tend to find prominently in the consternation of beginning students is like, the Zariski topology. I hate it. because it's just so, but it's a necessary evil. So, because you need topology. Otherwise, studying continuity is a real pain, you know?